So I think my screen is visible to all of you. And before starting this session, I would request everyone to go to this folder, and there I have uploaded one file. Okay, so this file that you should download it. Today we are going to work on this file. So week 5, day 02. Okay, so everyone download this folder and unzip it in your run folder. Okay, so please download it and unzip that folder. And if you have done this, then this many folders you have available. Okay, so I think this folder and this two one is not available. Other these three folders you have available at this. If you have correctly unzip that folder, you should have this 6 folder. These two I have added later before uploading on the MS Team. Okay, so let me first tell about this. So this I have already explained about the simple algorithm in the last class. So I've just written the different steps here. Okay, so I have also uploaded the PDF file on the in semester. So you can just correlate the things. Okay, so the different steps I have taken. What are the assumptions that you are taking? And here we solve about the P by row. We don't solve about the pressure field. Okay, because we are ignoring the transient term, so that is why you can means the momentum equation and the continuity equation you can write in terms of the P by rho. Okay, that is why you can solve in terms of the P by rho. Okay, and these are the algorithm that you need to follow, and you can simply correlate with the PDF of the algorithm PDF I have uploaded under MST. Okay, and here I have given some different means requirements here, and easily you can correlate these things. Okay, please try to go through this file. Okay, and try to understand this simple algorithm, simple scheme. Okay, since I have already explained simple algorithm and I have already coded this algorithm, that is why I'm not going to give means more time here. Okay, and also you can go through my YouTube channel, and that is already given how I have coded this simple scheme. Okay, so if you have understand my last class, it is not much difficult for you. This is just simple. So starting from this momentum equation that you already know, this is the momentum equation. Okay, where we are not taking consideration of the means transient term, because it's, simple scheme is for the uh, simple scheme is simply for the this steady state. Okay, so this if you know about the momentum equation has a convection term, diffusion term, and the pressure gradient. Okay, so this is where UE equation has been written. Okay, we have calculated the A, that I have told you that these two terms, that is the UE equation.A and UE equation.H, it is particularly defined in the OpenFOAM. Okay, it is not defined in the other CFD softwares. Okay, so using this A, we have calculated A inverse. Okay, see, we means this UE equation.A particularly calculates only the diagonal elements. Okay, so that is why it is easy to calculate the A inverse equal to 1 by A. Okay, because it has the diagonal elements only. Okay, so if you know about the matrices, that we can easily calculate the if means A inverse of any matrix if it has only diagonal elements using this formula. Okay, now this is I have calculated H by A, so that is A inverse into the H. Okay, so H is this component. Okay, now we have means this is the volume vector field, so we are using this so this is the volume vector field, so we converted it into the surface scalar field. Okay, and this is the pressure means a Laplacian equation for the pressure. that we have see that how we have derived these equations. Okay, so if you have watched my last tutorial, so this is a simply pressure character equations. Okay, and if we required, we means we need to provide some reference value for the pressure, and here we are solving the pressure equations. Okay, if you need, you can add the relaxation factor for the pressure field. Okay, and this is where after correcting the pressure, we are solving for the UV equation. Okay, and this is where we are calculating the phi. So remember, I told you this, what is difference between this phi and u. Okay, so here that we are calculating, this is the kind of the divergence of the u square. Okay, so we are taking one phi, that is the u from the previous iteration, and this is the u for the current iteration. This is the way of means making it linear. Of the This is the non-linear term under the momentum equation. So this is the strategy that we have used, that we are taking the phi from the previous iteration and u from the this iterations, and this way this terms has been means we make this into the linear term. Okay, so that is the strategy that we have used, and this is the u correct boundary condition data. This function we are going to see today, that how where from where this correct boundary condition comes into this picture. Okay, so this correct boundary condition is something related to the boundary conditions, boundary field, that we are going to discuss today. Okay, and here we are again means storing the p equal to p old equal to the p because for the relaxation factor. Okay, so this is the simple algorithm, and I just written in a simple scheme. Of course, if you see simple scheme in the OpenFOAM, this is a little bit complex. But if you want to understand the simple algorithm in the from the basics only, means basic terms involving these steps only, then you can go through this file. Okay, and of course, if you want to understand advanced simpleFOAM, then you can go through the OpenFOAM simpleFOAM. In present OpenFOAM simple scheme, the simplex scheme is also coded with the simple scheme. Okay, so this is something I want to code in the class, but due to the lack of the time, we are going to the boundary condition directly. Okay, so I will suggest that please go through this file and try to run this file and also solve it on the this test case that I have given the test case here. Okay, now let's go to the boundary condition. Okay, so I think in started class or day before start, I've already started something about the boundary condition. So you have already, I think you have quoted one boundary condition, that is the parabolic boundary condition. So in today class, we have a little bit theory, and we will understand it how boundary condition is related to the internal field and the geometric field, and how these things are coded in the OpenFOAM. Then we are also going to do some of the other coding related to the boundary condition. Okay, so we are going to also develop some of the boundary condition, but before that, we should understand that how this boundary condition evolves in the OpenFOAM. Okay, so everything start from the geometric field. Okay, so let me parallelly also go to the Doxygen. So you can type in the OpenFOAM Doxygen 6. And you can go to the 6 only. Okay, so here if you type geometric field, then you will have this file. Okay, so we are going to discuss about this geometric field in more details, in more depth. So specifically open about the geometric field, it has two different sections, that is the internal field and boundary fields. So we can say that everything, whatever the solver we solve in OpenFOAM, that basically solve for the geometric field. Okay, and since we are focusing on the boundary field, so boundary field means is related to the boundary face, and internal fields related to the volume center. Okay, so whenever we solve some governing equation, so for boundary field we solve for the boundary faces, but for the internal fields we solve for the mainly volume center. Okay, as long as we are not calculating some surface scalar field. Okay, so for example, so if you see vector field, so vector field is also defined as the volume vector field. So it is also related to the cell center of the given mesh. Similarly, for the scalar field, so it is also related to the volume scalar field. Okay, so this whatever wherever you found this term, that is the volume or VOL in OpenFOAM, this is known as the VOL scalar field, then these things are associated with the cell center. And as long as you have a surface scalar field, then it is associated with the face center. Okay, so I think this cell center and face center, at this situation we have correctly understand it, what is this cell center and what is the face center. Okay, now there are different terms that is related to the boundary. Boundary means geometric field related to the boundary field, that is the boundary mesh, boundary field and boundary field reef, that we are going to discuss, and we are going to see this on the Doxygen also. Okay, but these three things are important here. Okay, I'm going to show you this the codings on the Doxygen. Okay, so but first let me go through some of the slides and let me explain that what is the geometric field. Okay, so we can draw pictorial view of every mesh. Okay, so this complete things, the mesh you see in your mesh test case, this is kind of one mesh, and this complete thing is termed as a geometric field, and it has some internal field and it has some boundary field. So boundary field is related to the this, we can say the boundary faces, and internal field is related to the cell center. Okay, now for means for coding purpose of the boundary field, everything either you have a FB patch field or if you have a point patch field. Okay, so FB patch field is related to the every field that is for the cell center. Okay, and if you have some term related to the point patch field, means if you are if requirement has that, if you want to store some value at a point of this cell this given cell, then you need to have means code at the level of the point patch field. Okay, so that is point patch field is something related to the dynamic mesh movement, and in today's class we are not going to focus on this point patch field, we are only focusing on the FB patch field. Okay, so most of the finite volume boundary condition we are going to work on, this is these things that we need to understand, that is the FB patch field. Okay, we are going to see this FB patch field also. So basically we can draw some picture like, so mesh has either boundary or internal field, and this boundary and internal field is related to the geometric field. Okay, so this mesh has the field, so we are talking about the field, we are not talking about the mesh object, we are talking about the field object. So if you have a mesh, you will have a some field. So we are discussing about the field that is stored in the zero folder. Okay, so that can be either internal or boundary, and whatever means operation that we want to perform, that is related to the geometric field. Okay, now in geometric field, this boundary field has defined as the nested class, and I think you have some basic idea about the nested class, and this internal field is means defined as the derived class. Okay, so in means in so it means as I told you that this geometric field has different kind of the field. Like if you have a line mesh, then you can have a line field. If you have a volume mesh, then you can have a volumetric field. Okay, so this in OpenFOAM, these are the different kind of the field is there. So if you have a cell center, then you can define for the cell center volume field, and it is either can be a volume scalar field or the volume vector field. Okay, and it is applied to the cell center here, means, and for the boundary condition it should apply to the face center. Okay, and for the face center, if you want to define some field, then it should be surface, and you can have a surface scalar field. Okay, and it generally stored on the face center, so we don't need to worry about the boundary patches here. Okay, because it automatically stored for the face center. Okay, and if you have some point field, as I told you that, then you can either define as the point scalar field or the point vector field. Okay, so means this is means this field is something related to the what kind, means where you want to store it. If you want to store it on the cell center, then it should be volume. If you want to store on the face, then it should be face center, and if you want to store at the point, then it should be point field. Okay, so this is these things means we have already means explained in the last class, means last slide. Okay, Now if we see this geometric field, so this is .h of the geometric field. Okay, and if you see here that there are this geometric field is derived from this dimension field. Okay, so dimension field, it is derived from dimension. As I told you that in geometric field, the boundary field, that whatever the boundary field is available here, that we are coding as a nested class. So this is called as a nested class. If you are defining some class within the function of a class, then it is called as the nested class. So this is, we can see here that this is a kind of the nested class, that is the class boundary. And as I told you that internal fields are derived from the dimensional fields. So this is where we consider the internal fields. Since we are deriving this dimensional field in the geometric field, it means that we are already calling the specification of the internal field within the geometric field. Okay, see, it has the dimension field has the capability of the internal fields. So from this point, we are deriving this dimension field into the geometric field. Okay, so that is what I have written here, that internal fields is derived from the dimension field. Okay, okay, and why this has means internal field is derived from the dimensional field, because there is some reason, and maybe you can see in the means upcoming slides. Okay, so this is what I written here, that if you see the class of geometric field, you can see that it is derived from the dimension field. Okay, and this type can be anything, like it can be vector field, or it can be scalar field. This is the type, and this is the mesh, that what kind of mesh you want, like you want a volumetric mesh, or if you want to the surface mesh. So these two things is something related to type, is related to the what kind of the volume field you want to write here, and this geo mesh is related to the what kind of the mesh you are putting here. Either you are taking a point mesh, or you are considering it as a volume mesh. Okay, so this is you can see here that this geometric field has been derived from the dimension field. Okay, now here you can see that what is the advantage of the deriving internal field from the dimension field. Okay, so a dimension field is a generic class, okay, that represents the fields associated with the physical dimensions, such as the length, width, means. So this dimension field it means it expressed in the dimension. Okay, so what is the length, time, velocity. Okay, and it makes sure that it has some physical units, and it has some physical dimension. Okay, okay, so when you perform some arithmetic operations, such as the adding two fields or multiplying a scalar on a geometric field, the operation are applied only to the internal fields. Okay, so whenever do some operations by default, because without calling any reference to the boundary condition. So whenever we write suppose in some coding we write u equal to the u1 plus u2. So that is the, you want to add two value vector quantity. So as long as you are writing only u equal to u1 plus u2, it is going to work only for the internal field. It is not going to the work for the boundary field. Okay, so that is why this boundary field is coded as the nested class, whereas this internal field is derived from the dimension field. Okay, so and it makes sense, because if you are writing in some code equal to u1 plus u2, and it is going to also work for the boundary condition, then whatever the means condition that you have given in the zero folder, it is not going to work on those conditions. Okay, so that is why this is requirement of this boundary condition and internal fields. Okay, so whenever you do some parameters, so what I mean to say, that suppose you solve some like, so suppose we have some operation like p equal to the alpha p and 1 minus alpha into the p volt. So if we are doing this operation on the pressure field, so this is only going to work for the internal fields only. It is not going to work for the boundary fields. Okay, and it is because suppose that you are specifying some condition at the boundary field. Suppose you are specifying that this inlet has the fixed value equal to the 2 meter per second. Okay, or 2 Pascal, suppose you are specifying. So if it is going to work for the boundary condition, then whatever the boundary condition that you are applying at that patch, that is not going to work. Okay, so that is why whatever the operation you are doing within the solver, that should be only applied to the internal fields. Okay, that is why this is requirement here. So whatever the means arithmetic operation that you are doing on the geometric field, that should work only for to the internal fields. However, if you want to do the modification, suppose you solve some governing equation, and using that governing equation that you want to correct the boundary equation, so there is one function that is the correct boundary condition. Okay, so that function you can call, and I can show you that function here also. So this is the correct function. Okay, so this is where this is going to call for the boundary condition, and it is going to the correct boundary condition based on the specification that you have given in the zero folder. Okay, so that correct function is coded for this boundary condition, and it is the part of the nested class. Okay, so that is the here is the boundary field is created, and this here you can see here that this boundary field is derived from the field. Okay, so field is the means a number of so here we are calling field means you are calling the number of field within the boundary condition. Okay, so this is the a number of type of field is coded here that is being called in the boundary here. Okay, and we are here calling the mesh. Okay, so this is the mesh object. Okay, and these are the some constructor that we have created for the boundary. Okay, this is criteria if you want to read the boundary condition, and this two function that we generally use to update the coefficient and evaluate the boundary condition after correcting the means after solving some governing equation. So if you see this correct boundary condition, okay, so you can see here that this evaluate function is again been called here. Okay, so what is this evaluate function and what is this means update coefficient function? We will see in means I have given some points about this evaluate function and this update coefficient function in the upcoming slides. Okay, so this thing you can see here that whenever you solve some equation, we generally call this correct boundary condition, and that is one method in the geometric field. Okay, so these things don't touch the boundary condition. This whatever the operation that you see here, this don't generally touch the boundary condition. If you want to correct the boundary condition, then this two function is generally called in the OpenFOAM. Okay, so this all things I have means just whatever I explained on the slides, these things explained under Doxygen, these things I have written here. Okay, so these things that is the complete class structure of the geometric field. Okay, so this geometric boundary field is derived from the this geometric field, and this geometric boundary field is again derived from the field. Okay, so as I told you that this field is the collection of the boundary fields. Okay, and means this is the patch field from which is which is the part of the this field, and this patch field is where that you this fb patch field or fb point field comes into the picture. Okay, so you can see that this patch field has this evaluate and update coefficient. Okay, so even if you see this fb patch field, if you see this fb patch field, so you can see here that this update coefficient, and similarly there will be evaluate function will be there. Okay, So this is also this update coefficient and evaluate function is also part of this patch field, and this is where we are going to work if you want to do some modification in the boundary condition. Okay, so generally if you have done a started class, you can see that you work in this update coefficient function. And this evaluate function, there is a slightly difference between this evaluate and update coefficient. Okay, and as I told you that this correct boundary condition has the this evaluate function is being called. Okay, and you can see here that this is derived from the this type and value mesh, already told you that. Okay, and this declaration of this internal field you can see in the fb patch also, or geometric field also. Okay, so you can see here that this is how this internal fields is declaration is given here. Okay, so this type def that this type is and geomesh is not defined, so it can be any kind of the this field can be there, like this is can be a volume vector field or volume means this color field, and this geom is something that is related to either it is for the cell center or it is for the volumetric mesh. Okay, so these things that you can access here. Okay, so this all of information that I'm telling you. So this means the point is that you can whatever the operation that you are performing from the geometric field, this operator only works on the internal fields, and if you want to do some modification on the boundary condition, then you have to call the some method that is coded in the geometric field. Okay, and as I told you that the difference between evaluate and update coefficient, that so this means evaluate this member function called the init evaluate member function of the fvPatchField, and if boundary condition has not been initialized, so this evaluate will be called. Okay, so it means that this function will be called once. Okay, and if this function is called and if this is not initialized, so this if it is not initialized from the zero folder, then it is going to be initialized in using this evaluate function. Okay, so and this also works for the parallel communications. Okay, so and update coefficient, it is going to loops over the all patches of the geometric boundary field. Okay, which is referred to as the this. Okay, so this is the pointer this. Okay, and it is called directly for each element of the domain boundary using this operator. Okay, so this operator is going to assign each element of the boundary. Okay, so suppose there is a different n number of the boundary field is given here. Okay, so this operator is going to work for a n number of the boundary field here. Okay, and this is means this member function just check that whether this evaluate means this function is initialized for the every patch or not, and this is going to loop over the every patch, every phase of the given patch. Okay, so this is a slightly difference between the evaluate and update coefficient. Okay, so generally whenever we go to the means do some means boundary condition modifications, so we work for this update coefficient. Okay, so because we don't need to worry about the initialization. Okay, we want to apply some of the means some of the member function to the given patch. Okay, so that is why we work on the update coefficient, and this is something related to the initialization of the boundary condition. Okay, and this is you can see here that how this update coefficient is given here. So you can see here that this operator is being called for the patch I, and this is going to update the coefficient. Okay, now this update coefficient, that is something means based on the boundary condition that you are applying. Okay, so here you can see here that this is the template. Okay, and here you can see that you have called the geometric field. Okay, and inside the geometric field, this is the update coefficient function, and first it is going to check that whether you are applying correct boundary condition or not. If it is not, you are not applying, then it is going to show you error. Okay, and this you can see that this is the pointer which is going to work for the given patch. Okay, where you want to apply the boundary condition. Okay, and based on this operator, that this operator is applicable, that it is applying the update coefficient method, and this update coefficient is going to work based on the boundary condition that you are coding. Okay, so this is that you want to code from your side, that update coefficient is being called. Suppose you call the fixed value boundary condition, so this update coefficient is called from the fixed value, and it is going to apply to the patch I. So this is how this update coefficient works into the geometric field. Okay, so this update coefficient that is coded in the geometric boundary field, and this is where you are going to write that what kind of the update coefficient you want to work on. Okay, so I think this is clear to you. Okay, so this update coefficient is from the geometric boundary field, and this is point where you are going to code for the update coefficient. Okay, now here another major difference between the evaluate and the update coefficient that. So the major difference is that evaluate can be called an arbitrary number of times in a single time step. Okay, but it is going to execute only once. Okay, because initialization of any boundary field is should be called only once. Okay, so if it is already initialized, then there is no value of evaluate method. Okay, so that is why it does not matter how many numbers of how many times you are calling this evaluate, it is going to only execute only once. Okay, but if you are calling this update coefficient, it is going to work whatever number you are going to call. So if you call n number of times, it is going to work on the n number of times. Okay, so this is the major difference between the evaluate function and the update coefficient functions. Okay, so if you want, you can see this evaluate function here. So this is evaluate. Okay, so you can see here that what I want to show you. So you can see here that first stage it is going to called init evaluate. Okay, so if it is going to check that whether this boundary patch has initialization of the value has been done or not. If it is going to done, then it is not going to update the value. Okay, so if this function has been already called, then it is not going to do execution any further. Okay, so this is what I have written on the slide. Whereas if you are going to see the update coefficient, so this is the simple update coefficient function. So first it is going to check the debug, where means you are using the correct boundary condition or not. Okay, if it is correct, then it is going to do this iteration. Okay, so for every patch wherever you are applied this given boundary condition, so using this operator, it is going to modify the, or it is going to update the coefficient of the given value. Okay, so this is something from the something difference between the evaluate and the update coefficient. Okay, now if you want to see that whether this definition has been given, so this is the GeometricField.H, and if you go at the last, you will have geometric sorry, so you should go into the .c folder. So you should go to the geometric .c. So this is the .c. You can go to the source file. Okay, so here you can find that whatever the means method that has been coded for the boundary field, that is included with this .c extension. Okay, so here are the method that is related to the boundary field is given here. Okay, So you can go to and you can find the evaluate function on the update coefficient function. Okay, but you don't need to go in the much depth. You just need to understand the different functionality of the given function level. Okay. Now, so this is all something related to the geometric and boundary field. Okay, so I think you have now correlate between that how geometric field is related to the internal field and boundary field, and how this boundary field from the geometric field is related to the fvPatch field. Okay, so now I think we can understand the different boundary conditions. So if we speak about different boundary conditions, so we have generally the three types of boundary condition, and this couple type of boundary condition that is related to the patch to patch information. Okay, so either we have a fixed value boundary condition, or we can have a gradient type of boundary condition that can be either zero gradient or the fixed gradient, or we can have the mix of this both. Either this can be fixed value or it can be the mix of the gradient. So like if we have a heat transfer through the side walls, so there is a temperature gradient inside the given mesh, and there can be the convective heat transfer at the side walls. So that is kind of the Robin type of means boundary condition. And this patch to patch boundary condition, as I told you, that if you want to means share the information between the patch to patch, like a cyclic type of boundary condition or the periodic type of boundary condition, then it is known as the couple type of boundary condition. Okay. So first of all, if you want to do some means boundary condition modification, then either you can use the spec_foam. That is one other means one kind of utility, and maybe I can share you file. I can share you file how you can install this spec_foam, and I can also tell you that how you can use this. There is a utility known as the Groovy VC. Okay, Groovy VC is a Groovy boundary condition that you can use for means your purpose. So there is no need to always do the coding for the boundary condition. Yes, I will share you the instruction. So this swag for foam is a means this is the kind of a means open source file. If you install this swag for foam, there is a utility known as the Groovy VC. So using this Groovy VC, you can, as long as I know, means I have done for this mixed type of boundary condition also. I have also done this fixed value type of boundary condition, and you can simply use this Groovy VC kind of boundary condition using the swag for foam. And you can, if you don't require any hard coding, then you can usually use this Groovy VC boundary condition. Okay, so let me share you one example here. So I have worked for my project, so I can show you. Okay, so PSG work. So for temperature equation I've used, sorry. So see, this is how, this is I've used like a convective heat transfer through the sidewall. So using such a simple small number of lines, you can use this Groovy VC, that is the utility of the swag for foam, and that you don't need to code a means complete boundary condition. You just use a couple of lines, and you can use this swag for foam for your own boundary condition. So I can teach you that how you can install this swag_foam, and maybe I can show you that one or two examples. So first, try to install this swag_foam. I will attach this file. That is the swag_foam zip file, and I will also give you instruction how can you install it, and try to install that. And we can see that how this Groovy VC. There are other couple of utility also, like you can initialize the means field value. Okay, so like there is set field utility in the OpenFOAM. Similarly, there is a function set field in the open this that maybe I can show. So that so there is, means I just want to say that there is no need to always do coding. So if you have a this function set field dict object. So for example, you can see that I wanted to initialize the porosity value at the different location. So using just a couple of lines, you can do these things using the function set field. Okay, so always there is no need to do the coding for the boundary condition. Okay, but if it requires, you can do from your side. Okay, so that is what we are learning here. Okay, so first see the boundary condition that is available in the OpenFOAM. Okay, so if I want to show you 1 minute. So if you see OpenFOAM directory, so there are subdirectories of the OpenFOAM boundary condition. Like there is a basic constant type of boundary condition, derived type of boundary condition, fvPatchField type of boundary condition. So if I show you in the src folder, okay, so we can go to directly open the terminal, and I can type F6. Okay, and if I go to the FOAM src finite volume fields, okay, sorry, ls, I need to do the ls. So you can see that we have basic boundary condition, constant boundary condition, derived boundary condition, and fvPatchField. Now what are these different classes are there, different folders, different directories are there. So this fvPatchField generally have the class definition of the boundary condition. So this fvPatchField is means something related to the geometric field. Okay, so whatever the class definition related to boundary condition are given, so these are given in this fvPatchField. Okay, so this has the main function and data structure that is going to use for the this basic boundary condition, this class constant boundary condition and derived boundary condition. So this is the general class definition of the boundary condition that you can find in the fvPatchField. Okay, now speaking of the basic, so if you see the basic, okay, so we can see the basics. So you can see here that generally this Dirichlet type of boundary condition, Newman type of boundary condition, and Robert type of boundary condition you can find in the basic folder. Okay, so we have a fixed value, mixed value kind of boundary condition, fixed gradient type of boundary condition, and additionally you can see that there is a couple type of boundary condition. So you can, as I told you, that couple type of boundary condition that you want to share the information between the patch to patch. Okay, so means one type of boundary condition of this couple type is the constant boundary condition, that is the periodic boundary condition. Okay, so this is one example. Like if you want to share the periodic boundary condition between this patch to this patch, okay, and this is the outer ball. Okay, so you are sharing the information from this patch to this patch. This is kind of the periodic boundary condition. Okay, so this comes within the couple type of boundary condition. Okay, so this periodic boundary condition is a type of a couple type boundary condition. Okay, now there is a derived boundary condition that is generally basically derived from the basic boundary condition. Okay, so we can list some of the derived boundary condition. So you can find a year number of the boundary condition that is derived from the basic boundary condition. Okay, so either it is the mixed of the means basic plus fixed gradient, or it is the kind of the Robin boundary condition. So you can find the m number of the boundary condition that is coded here. Okay, we will see some of the examples here, and we will see in the depth out of this boundary condition that is coded here. Okay, so speaking of the mathematical expression, so let me first go to the earlier slides. Okay, so means if I told means as I told you that this mixed boundary condition is means the combination of the fixed gradient as well as the mixed value. Okay, So this is one example, that is the mixed fvPatchField. Okay, so you can see here that if you see the code of the mixed fvPatchField, so it has the means three value, that is the reference value, ref grade, and value fraction. Okay, so this ref value, ref grade is something, what is the something related to the field type. So if you want to give some gradient, and suppose this field is related to the volume vector field, so here you are specifying the ref grade equal to the gradient value of that specific field. Similarly, for the ref value, if you want to give some value of that related field. Okay, so if you want to give the volume scalar field, so there is some value equal to the means field value, and this volume fraction is something related to the scalar field, that is kind of the source value. Okay, so this using the mix fvPatch field, and if you know this exact value of this ref value, ref grade, and value fraction, you can code the n number of the boundary condition. Okay, so for example, there is one example of inlet outlet fvPatch field. Okay, so for this specific this inlet outlet patch, there is a ref grade equal to 0. Okay, that is kind of the field type that you want to, means this inlet outlet can be applied for the either vector field or the scalar field. So that is type that you can specify based on your, means for what purpose you want to use this boundary condition. Okay, and means what is the, so let me show you this inlet outlet boundary condition. So if you go to the OpenFOAM 6 src, and if you open the finite volume, so there is field, and there you can find the this fvPatch field, and here you can have this boundary conditions that is given here. Okay, so if I go to this derived boundary condition, there is an inlet outlet boundary condition. Okay, so that is something coded from the mixed type of boundary condition. Okay, so if I open the this text file, okay, so this is where you can say that, as I told you, that everything different type of coding is given in the this update coefficient member function. Okay, so whatever the value you want to update using that given boundary condition, that you are going to update using this update coefficient member function. Okay, so if it is already updated, then it this function will return. Okay, otherwise it will going to do this parameter, it is going to take the 5 value. Okay, and based on the 5 value, it is going to specify the volume fraction of this given patch, for what patch you want to solve, you want to apply this inlet outlet boundary condition. Okay, so that is, you can see that code is that the same code is written here. Okay, so this inlet outlet boundary condition is derived from the mixed type of boundary condition. Okay, and you can see here that means same code that we are calling, we are calculating the 5 value of this given patch, and based on this 5 value, we are changing the value fraction. Okay, so what is the purpose of this inlet outlet volume means inlet outlet boundary condition? So it is going to assign 1 if the flow direction is outflow. Okay, so if the flow direction is outflow, then the value is going to assign equal to the 1. If the flow direction is opposite of the outflow, okay, so the support direction in the right word, and the calculated value is means inside the boundary face, then it is going to specify the 0 value. Okay, so that is a purpose, that is why this phi is being calculated. So based on this phi value, it is going to check that whether the flow is outward or whether the flow is inward. If the flow is outward, then it is going to assign the 1, and if it is the means it is not outward, then it is going to give the value equal to the 0. Okay, so how this means, this is the way it is going to assign the value equal to the, so this pos function, that is the POS. So this pos function taking the this phi name scalar quantity that you are calculating here. Okay, so means this, we are taking a scalar quantity, and we are passing this as a argument in this function, that is the pos 0. Okay, and here this you can see here that conditional function is applied here. Okay, so it is saying that if yes is greater than equal to the 0, then return equal to the 1, and if it is less than 0, then return equal to the 0. Okay, so I think this you can relate here. This is simple C++, means simple C++ code is written here. So based on this scalar yes value, if yes is greater than the 0, then it is going to implement equal to the 1. So greater than 0 means that phi value equal to greater than 0. Otherwise, it is going to imply equal to the 0. Okay, that way you can see here that. Now here you can again see that this value function means this function is being called. Okay, so this is a function of the mixed fvPatchField. Okay, and using this this value function, we can update the value of the given patch. Okay, so I think this you can relate here. This how this inlet outlet of inlet outlet boundary condition works. That I think you can relate from this syntax code that you can see here. Okay. Now there are some other important function, that is the value internal coefficient, value boundary coefficient, gradient internal coefficient, gradient boundary coefficient. Okay, so these four functions are very important for the this derived boundary this basic boundary condition. Okay, so whatever the these functions that you are seeing, suppose let me give the example of the zero fvPatchField. So if you see here that, so you can see here that these are the functions that you are seeing: value internal coefficient, value boundary coefficient, gradient internal coefficient, gradient boundary coefficients. Okay, so if you want to understand this boundary condition, that is coded in the basics of the means like the Newman boundary condition or Robin boundary condition, then this member function is important. You should understand what are these member functions. Okay, so first you should understand that you can, if you want to write Dirichlet type of boundary condition, this is the way that you can write. Okay, so phi can be any quantity, either it can be temperature or it can be any kind of quantity can be there. Okay, similarly, if you want to apply the Newman type of boundary condition, so this is a kind of the gradient boundary condition. Okay, so if you have some gradient value, then you can write this as a, so d phi can be diffusion coefficient. So if you want to have a temperature, this k is a thermal diffusivity. Okay, phi is temperature, and here qb can be heat transfer, heat flux. Okay, so phi can be any quantity, either it can be temperature or any kind of the quantity that you can write here for the Newman boundary condition. Okay, mixed boundary condition is kind of the, I have taken one example like convective heat transfer. Okay, so you can see here that whatever the boundary condition if you want to write, it has either the advection term or it has a divergence operator or it has a Laplacian operator. Okay, so this is kind of a Laplacian operator. So if you want to write any type of boundary condition, then either it has a advection divergence term or it has a Laplacian terms. Okay, so this out of this four member function that is the part of the fvPatchField. So this function, that is the volume internal coefficient or volume boundary coefficient, are generally related to the divergence operator. Okay, so whenever you want to linearize the divergence operator, then you are going to means account for the this volume internal coefficient or volume boundary coefficient. Okay, and if you want to linearize the Laplacian term, then you should have gradient internal coefficient function or the gradient boundary coefficient functions. Okay, so suppose we are taking the examples of the, so suppose we want, so this is whatever I have written here, that I have given in the form of the table here. Okay, so for the divergence terms, we should have a this diagonal coefficient should have a volume internal coefficient, and for the source term, we should have a volume boundary coefficient. Okay, and for the Laplacian terms, we should have a gradient internal coefficient and the gradient boundary coefficient. Okay, so suppose we want to see this coding further, this zero flux, that is the zero gradient boundary condition. Okay, so zero gradient boundary condition means that we should have only this phi equal to the phi specific. Okay, so we should have we don't have any means any source term, we don't have any Laplacian term, we don't have any Laplacian source term. Okay, we have only phi b, that is we have a only diagonal coefficient. Okay, so out of this four values, only we should have this value internal coefficient, that is the value equal to 1. Okay, other source term, other terms should be 0. Okay, so if you see the codings here, okay, so you can see here that this volume internal coefficient for the zero gradient empty patch field equal to the 1, and for the value boundary coefficient this is equal to the 0, and for the gradient internal coefficient this is equal to the 0, and for the gradient boundary coefficient this is equal to the 0. Okay, so other terms you can see here that are the terms are the 0, only this volume internal coefficient equal to the some values. Okay, so this is means this is the way of the this means you can see this different basic type of boundary condition, and you can see this four function is vastly used in this means basic type of boundary condition. Okay, so this is something that I wanted to means this you should we don't need to means under we should have only concept about this thing. We don't need to, we are not going to use this member function for our means our development of the boundary condition. Just I wanted to I wanted to let you have some idea about that how this coding has been done in the OpenFOAM for the basic type of boundary condition. Okay, I think up to this level you have a clear picture of that what are the this different boundary condition are given here, what is this fvPatchField, what is the described boundary condition, what is the constant boundary condition, and what is the basic boundary, and what are the this different member function, what is different between the update coefficient, and what is this evaluate member function. Okay, so if everything is okay till now, so we can proceed for the some boundary condition development. And if you want to have some more idea about the different boundary condition, so I have attached one PDF file, and you can see here what is the by default boundary condition is available here, and what is the means functionality of this boundary condition, that you can see from this PDF file. Okay, okay, you can see that what is how this is going to works, and how you can code this different type of the boundary condition we can see here. Okay, so you can go through this file, and you can, so standard boundary condition are given here. You can just so for the flow and energy there are different number of boundary condition. For the turbulent condition you can have boundary condition. For the wall function you have a number of boundary condition. For the heat transfer condition we have a number of boundary condition, and for the radiation purpose also there is a number of boundary condition. Okay, so please go through it, and you can choose based on your choice whenever you want. Okay, because it is around 133 page, so better to use whenever we want to use this file. So just to search for that boundary condition. For example, if you want to see zero gradient, okay, so page number 95. Yes, zero gradient. So this is shown that how you can use the zero gradient boundary condition. Okay, so since zero gradient is the basic boundary condition, there is no specification is given for that, because there are some turbulent boundary condition, that is the ATM boundary condition layer in it epsilon. Okay, so you can use this as a standard file for your purpose. Now we can start some coding part. So then, for what purpose you want to install the OpenFOAM extend? Means why you want to install this foam extend version? Okay, okay, okay. So far, I think he might have mentioned about for the dynamic mesh movement. Yes, yeah. I will ask him to means tell you about that how to install the foam extend. So he has used for the means for the dynamic mesh movement purpose. He has used the foam extend version. So I think that is why he may mentioned about this foam extend. Okay. Okay, so in the last class, you have already know how to do this, how to work for the my parabolic velocity. So we have means we started to work on this folder, and you have taken some variables that is like a private data, and you have some constructor. Okay, and then you have member functions to means to read the this private data that you have declared, and again there is a update coefficient. So as I told you that this is the important member function if you want to modify your boundary condition. So now we are going to uh, work for the paraboloid kind of boundary condition. Okay, so it means whatever things that I'm doing, just try to work by yourself. Okay, so we are going to copy this my parabolic velocity. Okay, and we are going to create paraboloid. These are the boundary condition we are going to create. Okay, so we are copying this my parabolic velocity into the my paraboloid velocity. Okay, so you can see here that there is one folder that is the my paraboloid velocity. So this folder that I have shared with you, I have just copied as a my paraboloid velocity. Okay, so we can see here that before starting we need to just rename everything. Okay, so first we will open the this files folder, and we are, instead of the my parabolic velocity, we are going to put as the my paraboloid velocity, and similarly we are going to rename it as a my paraboloid velocity BC. Okay, so as soon as you copy the folder based on your requirements, we need to change these things. Okay, so we are going to change this also, and we are going to change this also. Okay, so these things like we need to change the means files of the make folder, and these things we need to do as soon as you do the. Okay, now we can open it in the any editor. Let me close other folders. Okay, so this is the .c folder, and this is the .h folder. Okay, so first we need to change this my parabolic velocity into the my. So if you are using the Genie editor, then you can use the Control H. Okay, if you are using some other editor, so I think that is also going to work in the gedit editor also. So Control H is you can use for the changing every, so whatever the text that is the my parabolic velocity is written here, that is going to replace with the my paraboloid velocity. So you can press here in document. Okay, so you can see that everything has been changed. So my parabolic velocity has been changed as the my paraboloid velocity. Okay, so this is that we did in the .h folder. Similarly, we are going to do in the this .c folder. So after copying this, just press the Control H. Okay, and this you want to replace with the my paraboloid velocity. Okay, so again you can type the in this Control H and in this document. So you can see here that this my paraboloid velocity has been replaced from the this my parabolic velocity. Okay, so before doing some modification, we can go to the that folder and we can run. Before doing some modification, we should first check that whether everything correct or not. So at this level, we should check that it is working properly. Then we can do modification from our side. Okay, so I think everyone is means okay till now. So I think it means everyone is at this level. Everyone on the same page. Okay. Now we want to have this. This is the means. Let me show you the this text file. We want to code this boundary condition. So we should have. So now earlier in parabolic, means you was means that you want to code that is the 1D. So that is why this u has only one coordinate. Now we have two coordinates. Okay, and based on these two coordinates, we are going to calculate the r, that is the radius, and that is going to divide by the r max. Okay, and we are going to means subtract from this into the -1, and this r will be calculated from the this square root of the y square plus z square. Okay, so let me first show you the test case. So test case I have also given here. So you can go to the test case. Okay, so since for the meshing purpose we are using the .msh file. So this msh file is means exported from the ANSYS. Okay, so that is why we can use the code that is the fluent 3D form. This command you can use to export any mesh from the fluent. Okay, that is the means relative of the ANSYS. Okay, now we can call that mesh, that is the mesh, and the name of that mesh. Okay, this is the 3D pipe.msh. So this file you can call for the meshing purpose. Okay, so this is the command if you want to means convert mesh.msh file into the OpenFOAM meshing. Okay, so at this level you can see here that there is no any polymesh folder. Okay, so OpenFOAM means no have any idea about the meshing of the this uh, means a meshing of the given geometry. Okay, because we have exported that .msh file from the ANSYS Fluent. Okay, so this command you can use if you want to convert this ANSYS Fluent mesh into the OpenFOAM. Okay, so if I run here, so now you can see here that there is a polymesh has been created. Okay, now we can see the this open the paraFOAM. And I want to just show you only inlet. So we want to specify inlet velocity at this patch only. Okay, so you can see here that this flow direction will be into the x direction. Okay, so flow direction is going to be into the x direction. Okay, and the radius that we are going to calculate using the y coordinates and the z coordinates. Okay, so from the center of this given mesh, for every patch we are going to calculate the radius. Okay, that is going to the small r. Okay, and based on that small r we are going to divide with the capital R, that is the radius of this total this circle. Okay, and that means we are going to calculate u max 1 minus small r upon the capital R. So for every patch, every phase we are going to calculate the small r, and then we are going to divide with the capital R, and then we are going to calculate the this value. Okay, this u yz equal to the u max 1 minus r upon r. So that is why we need to have y coordinates and the z coordinates. Okay, so I think you have means you understand that what we need to do mathematically. You have understanding of these things. Okay, so let me show you in the dot c. So as I told you that this expression is going to remain the same. These things we are going to have the same because we are solving the same governing equation, that u r equal to the u max 1 minus r upon capital R to the square. Okay, so these things I think you have a better understanding about this expression because already you have quoted about this. Now only the difference that this r value will be differ from the parabolic boundary condition. Okay, so for that purpose we can calculate the first we need to have first we need to have coordinate y. Okay, that we are going to calculate coordinate y because we need to have this means for we need to have the y value, and then we need to have the coordinate z, and based on this y or z we are going to calculate the radius. Okay, so these things we need to calculate. So this coordinate y equal to the c, and the means dot product with the y coordinates. Similarly we can calculate the z coordinate z. Okay, so we can have dot product with the z. Okay, so we have this coordinate y and coordinate z. Now what will be the coordinate r? That is the square root of the, so this function that I want to say that this r equal to the square root of the y square plus z square. Okay, so this means that coordinate y into the coordinate y, this things means we are going to have coordinate y into the coordinate y plus coordinate z into the coordinate z. Okay, so this is going to give the coordinate r. Okay, so I think this you can better understand. Okay, this you can also better understand, but problem is that sometimes here suppose your center lies within the, so here your center is on the 0 0. Okay, so you can see here that the center is on the 0 0, and means z is also 0 and y is also 0, but sometimes it may happens that the center of the given circle, say center of the given patch is not lies at the 0 0. So in that scenario we should have the center value of the, so if we know the center value of the given patch, then we can subtract that value from this c value. Okay, so suppose we have information that this center value lies as the CTR. Okay, so we can subtract that value. Okay, what I mean to say that suppose if the center is light as the coordinate 2 and 3. Okay, so if we subtract this value from the c value, then we can means automatically multiply with the y dash, and we can have idea about the. Okay, so This way you can calculate here. Okay. So now we have coordinate y, coordinate z. We have calculated the radius, and based on this coordinate radius, we are calculating this, updating this value. Okay. So we have three variables. We have means created, sorry, two variables. So this CTR z and this dot z value. Means this z coordinates and this CTR, this two value we have new quantities. Okay. Now we need to have means add these quantities into the private value. Okay. So this z is going to has a vector quantity, and CTR is also going to have a vector quantity. So we can copy these two things. So we have taken one new variable, that is z, and we have another new variable, that is the CTR. Okay. So this variable is already taken from the last class. Okay. Now we have this constructor. Okay, different constructor. So now we should have this member function to access the boundary condition, to access this z coordinates, and similarly we need to access the CTR, that is the centroid. Okay. So this is all about the .h. So we have this centroid value, this z, that is the z coordinates. Y we have already means copying from the last class. Okay. Now we need to update this constructor. So this is the default constructor. So that is the z. We need to have a z coordinates 0, 0, 1. Similarly, we need to have a CTR, and this is also, this is by default we are taking as the 0, 0, 0 as a centroid. Okay. Means user can specify the centroid value in the means where he wants to means at which patch he wants to apply this boundary condition. So user can also specify this boundary condition. So if user is not going to specify, then it is going to call the default value. Okay. So this is, similarly we can call the pointer constructor. So this is the z, this is the CTR. Okay. Similarly we can work for this. So this is the z, and this is the centroid. So this is the constructor using the dictionary. Okay. Similarly we can apply this debug condition. So if this magnitude of this z applied is less than the given small value, then it is going to show the error. Okay. Okay. Similarly we can specify this constructor. Okay. And we have already completed our task here, and we can check that everything is working perfect or not. Yes. So everything is working perfectly. We need to also write this keyword here. Okay. So we need to we want to that it should print after every iteration. So why it is important? So why it is important? So whenever this another time folder is being created, suppose it is the 0 folder, it is going to be 0.1 or 0.2. So whether you want to write this values after every iteration or not, that is why we should write here also. Okay, so let me first show you without doing any modification in this write entry. Okay, suppose we are not modifying this write entry, and let me show you that what error we are going to get, then you should have a better idea. Okay, so now we have already created the boundary condition, and if you go to U, so that we have created, that is the my paraboloid velocity. Okay, so my paraboloid velocity. Okay, so U max we have given 2.0, R max that is the 0.5, and that is the means normal vector, and that is the Y value, that is the Z value. The center we are taking as a 0 0 because the center of this given message lies as the 0 0. Okay, so if we type here, suppose we don't know that whether our our means our test case can read this map paraboloid velocity or not. If you want to run here, 6 IcoFoam, so you can see here that this is showing the error. Okay, and whether you want to see that whether your solver can read this boundary condition or not, so you can see here that this my paraboloid velocity is already coded here. Okay, so it means that your boundary condition is already read by the constructor. Okay, so we can write so I think this concept is already explained by Abhishek. Okay, he's already told that if you want to add some new boundary condition, you need to add the this library here. Okay, so for example, I have after compilation, I have this my paraboloid velocity boundary condition.so, so that should be present here in the control dict file. Okay, then only your boundary condition will be read by the solver. Okay, so that I think yes, CTR is the centroid. N is the normal vector. Okay, so what is the N? N is specifying that in which direction you want to apply the boundary condition. Okay, so suppose you can see here that this N is equal to the 100. So it means that in the positive x direction you want to apply the boundary. So you can see here that this coordinate, so x is in the positive direction. So that is why this N is the normal vector in the direction of the in which direction you want to apply the boundary condition. So that is the flow direction, you can say, that is the N vector. Okay, and the difference between C and CTR is C is the suppose sometime it happens that patch you are taking has not the center at the 0 0. Okay, so in that condition you want to subtract this C, that is the C of the given patch, and that is the centroid of the given patch. Okay, you understand what I want to say, this C minus CTR? So C means so let me show you the code. C you are taking a volume vector field and patch.cf. So patch.cf, if you see our the boundary meshing class. So in that meshing class, I have shown you one folder where we have calculated the cell center of the every face of the given patch. Okay, so the patch for the given patch, this CF is going to give you a face center of the every faces. A number of faces are there. So here you can see that a number of the faces are there. So for every patch, it is going to give the a vector quantity. So that is what C is here. Okay. Now we are subtracting C minus CTR. So this CTR is the centroid of the complete face. Okay, so suppose the centroid is lies here 2, 3. Okay, so for this face we want to calculate the C minus C centroid. Okay, so it is going to be subtract from the centroid of the given patch, and that is we are going to means take the dot product with the y and take the dot product with the z. Okay, I think now it is clear to you that what is the difference between the CCTR and M. Okay. So now we can run IcoFoam. Oh, we are getting error. So what error could be there? Can anyone tell from your side what error we are getting? So there is no any error in the constructor. So I think there is error in the update coefficient only. So we have taken this C and we are calculating C minus CTR. C minus CTR, we are taking the dot product. Okay, sorry. This should be Z. This is this we are taking y square plus z square. Okay, so this should be y square plus z square. By taking coordinate z into the coordinate y, that is why we are getting the error. Okay, I think we need to recompile again. Yes, so then we have already. Now you can see here that our solver is running. Okay, now suppose in control dict we have a latest time, and suppose we close our solver here, and you can see here that now from the latest time, see what I want to show. So from the latest time we wanted to run, so you can see here that it start from the latest time. Okay, so from the latest time, if you want to run the solver, we are getting error that keyword j is not defined. Okay, so why it is showing the error? So if you go to the last folder here and you open this U folder, you can see here that it is calculating the value for different things, but for the inlet it is not going to define the different value. Where the definition is written here. Okay, so suppose here you can see here that this is the bounded definition for the inlet. So you can see here that you are writing the umax, you are writing the rm, you are writing the n, you are writing the y, you are writing the value, but you are not writing the z and you are not writing the CTR. So that is what it is showing the error, that you have not this z value and you have not this centroid value. Okay, so that is why you need to write here these things. Okay, because whenever you want to run this solver after the latest time, you are going to get the error. Okay, so that is why it is always better to write this value. Okay, so that is why we need to write this z value also. Okay, similarly we want to write the CTR. Okay, because if you want to run from the latest time, it is going to show you the error. Okay, now we can compile the solver. Okay, and first let me clean the only time. So if you want to only clean the times, we don't want to change the mesh, we don't want to change the zero folder, then we can run this command foam list times and rm. So it is going to only remove the time folder. Okay, so you can see here that there is no any folder related to the time. Okay, now you can run the IcoFoam. Okay, and now suppose we stop here, and if you again run the IcoFoam, so you can see that it is starting from the 0.3. Okay, so that is why you need to write every value at the this write function. Okay, so this is going to write into the given folder, and from that time step you can start your simulation. Okay, so now another boundary condition that we want to code, that is the time value parabolic boundary condition. Okay, so we want to code something like URT equal to the UR into the sine omega into the t. Okay, so this UR definition is going to remain the same. So this is the same definition that we are going to keep, that is the UR, and just we want to add the this sine omega into the time. This function we want to add. Okay, so these things we want to add here. Okay, so we need to have this time value and we need to have omega. Okay, so first let me show you that how you can call. So for that purpose, for calling a time, we can, if you recall our class on the this object registry, so you know that we can call mesh object or this any data information from the object registry. So if you want to show you that how this time is being called in the src folder, we can just use the grep command and this r command, and we can use this time. Okay, so you can see that a number of places as uh, time object has been called. Okay, so you can see that this is how you can call the time object. This is the database, and from this database you are calling the current time value. Okay, so this information we can use for creating one scalar quantity. Okay, so I think this BV you already means know about from the our object registry class. Okay, so from this database we are calling, from database we are calling the time value, and we can store as a scalar quantity. Okay, so we don't need to take another variable for getting the time, because we are taking this time value from the current iteration. Okay, so this information we are taking from the current time step. So we can take as a scalar quantity, and we can call that we are taking this from the database the current time runtime value, and we are taking as a scalar quantity. Okay, now we again need to have a omega. So this omega we can take as a scalar value from the user. Okay, suppose we are taking as a, so we can now multiply this with a sine, and this maybe we can take omega as a scalar quantity from the user. So that's this we can take omega multiply and this current time. Okay, so this is something we want to code, that sine omega into t. So pardon, we need to first we need to create some another folder. So I am copying first this paraboloid cp minus r, this my paraboloid, as a, maybe we can take as a time varying paraboloid. Okay, velocity. Okay, so we can do modification in this. Okay, so as soon as you copy this, we need to do the modification, and we can go to the make first, and we can uh, rename it as a time varying velocity. Here also we can copy as a time varying velocity. Okay. Similarly, we can open this two in the any editor. Okay. Now we can use this control H command, and we can change everything. So in document, everything has been changed automatically. Okay. Also, we need to change here also. Similarly, here we can change the. So now we can again open in the easy editor. So here we have already changed. We need to change in the .c. So here we can again use the control H, and in document we want to change everything. Okay. So before doing any modification, we can first go to the folder. Okay. And we can do wclean data. So you need to type F6 wclean.l wmake leave so. Okay. So now we can do the here we can take this scalar quantity, this current time equal to the this dv, this database. Okay. So this is just warning that we are not currently using this variable, that whatever variable we are taking, that we are not using. This is just warning. So I think everything is okay. Now we can do the modification. So we can take sign of this omega, that is going to be one scalar field, multiply into the this current time. Okay. So since we are creating this omega as a scalar field, so we need to means ask into the private member. Similarly, the scalar we can take omega. So this is a omega. Okay, that we are going to ask from the user. And similarly, this scalar function we can create one scalar function, that is the omega, and here also we are going to have this omega. Okay, so this is something in the H file. Similarly, we can go to the .c, and similarly from here we can copy and paste, and we can have omega. Okay, similarly we can have here also. So these things is just repetitive things. Okay, similarly from here also we can write it as a, we can take a read scalar, and we can look up for the omega. Okay, here also sorry. Okay, so here this is going to read this value, and using this value it is going to calculate these values, and we can again write these values, because as I told you that this is important if you want to Okay, so this is important if you want to uh, run from the any last time step. So I think we have done everything and there should be no any error. What error I am getting? Why this is error I am getting? Okay, I think we need to first calculate the value, then we need to apply this n operator. Yes. So actually, we need to first calculate the value. This is going to give you a scalar quantity. Okay. So based on this scalar quantity, we are going to apply. We are going to take product with this n dot, that is the normal vector, and then from that we are going to convert into the vector field. So that is why we are getting the error. Okay, because we were trying to means multiply as vector field with a some scalar. So this is why we are getting the error. So first we need to calculate the scalar quantity, and based on that scalar quantity we are going to apply with the we are going to multiply with the normal vector, and that normal vector is going to convert into the this vector field. Okay, so for that purpose we have another test case. So we can, if you open this, so we have already given this time varying parabolic velocity, and here you can see that the omega is equal to the 5. Okay, and since we have only modified this omega value, so we don't need to the add any other scalar quantity. Okay, now this should be present in the control dict. So if we go to the control dict folder, so this should be present here. Okay, so we can open this test case. Okay, and we can run FOAM6 and we can run IcoFoam. Saying that mesh is not created. So we can run fluent 3D mesh to foam mesh dot we have 3D pipe mesh. Okay, now we can run the IcoFoam. Okay, so I think some spelling mistake is there. Okay, so I can copy this. Time varying paraboloid velocity. This should be time varying wax mapped fixed value. Why it is creating like this? It should read like time varying paraboloid velocity. Hmm. Why it is not able to read this time varying parabolide velocity? Okay, so there was syntax error. That is what it is not able to read. Okay, so there was syntax error in the control dict, so that is why it was not able to read. Yes, yes. So Jumpseat it is essential because if you're not going to write control and z, then it is not going to run from the latest time. So as I told you, as I show you example also. Okay. So I think everyone is able to run the test case. So Siddhin, that things you are asking that what is the FBCV means something is this number, this variable is that. So there you can see that there is a number of the constructor here. Okay. So like this constructor is constructed from the patch and internal field. This is constructed from the patch, internal field, and external. Okay. So if you want to understand that this is constructed from the this means dimension field vector and this FB patch field. Okay. So this is just this is just taken as the variable of this type of the field. Okay. This is just a variable. Okay. For using this constructor, we are defining the different value. Okay. So for example, if you go above here, you can see that this is the one variable that is taken into taken consideration. Here you can take any kind of name, FB, FCV, PVF, that you can take any name. So there are a number of the constructor is defined. So this constructor definition is given here before the member function. Okay, so if you want to correlate with this, which this FCV, PVF is that, so you can see that this cloning is being done using this constructor. No, I think this constructor is being called. So this constructor is being called, so you can correlate with that thing. Okay, so this is the constructor that can be correlated with this. Okay, that is kind of the copy constructor. No, 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 no. This is just a copy constructor. So I think I've already give you a file that why copy constructor is important. So this things is just written here. So you can see that this is dimension field and this is the time varying parabolide velocity of vector patch field. So this is the. So I think everyone is able to do this two boundary condition, and we have already told you about the parabolic kind of boundary condition. Okay, so this is enough of up to this time if you want to do any boundary condition modification. So I'll means I will also share you that how you can use the swap-form, and which is very important utility. You don't need to do this number of modification. So even important boundary condition modification you can just write in 2 or 3 lines. Okay. Yeah, I have already shared in the doc file. Sorry, in a zip file that I have shared with you. Where is this? Here in the team, you can go and you can file here. So there is one zip file shared. This folder you can find this doc file, the PDF file, and also I will share the slide for the today. Okay. And another thing I want to point out that if you want to do modification, just copy any boundary condition folder into the run in your run file and just try to work by yourself. Okay, don't worry that it is going to means, but just you should focus that you should means you should modify here that this should be either user libin or this should be user app bin. Okay, because you should never change the default installation of the OpenFOAM, otherwise it is going to show you some error. Okay, so always you can do this user libin or user app bin, and you can do any type of modification, and you should play with the codings. Okay, so don't afraid that it is going to means it is going to show you a number of error. So don't worry about that, and you should means try to modify the things. Sometimes it is means always means beneficial that you should just print the things. If you find some error, so you can in the update coefficient member function, you can print info by using the info. You can see that means what error you are doing. So using this info command, and you can print the value, and if you want, you can learn. Okay, so this is the way of this is means a way of technique to either find out the where you are doing the error, or if you want to learn programming, this is one way you can use that. You can print the values, and you can check that whether you are doing right or not. Okay, so just means today I want to say that just if you are afraid of the coding, just start do coding whatever means modification you want to do. Okay, so means when I was learning, I just go to the src folder, and I first of all I take some any means suppose where is finite volume and fields this fvPatchField. So what I do, I just take the first learn the this whatever the boundary condition is given. So first I learn that what is the member function and whatever the different things are given here. Okay, so once I learn the things, then after this I just start doing coding from myself. Okay, so first learn from this test cases or from default boundary installation, and then copy that folder and do the means remove everything, and from your side you start coding by yourself. Okay, so this is the way you can means see the things that what are the error you are doing. Okay, so for this now I would like to stop here. If you have any question, you can write in the chat box. Okay, so thank you to all of you. So if any question anytime, you can write in the chat box, or you can write in the ask in the group, WhatsApp group. So thank you to all of you. Let me stop the recordings.